Hello, this is Jack Jackson. In this video, we're going to talk a little bit about finding area formulas for triangles and parallelograms. Now, we're going to assume that we know that the area formula for a rectangle is length times width or base times height, either way you want to say that. So we're going to start with a triangle. So we're given any triangle ABC here, and we identify one of the sides as the base. Let's call this side AC the base. Right now it's 6 long. It's dynamic here, so it'll change length as we move that around. Okay. Now, what's the next step? We're going to create a parallel line through point B parallel to line AC. We know we can do that by the parallel postulate. Next, let's create these perpendicular lines from A to this line up here and let its intersection be X, and a perpendicular here, let the intersection with that line and this line here be Z, and then make these line segments. So if you look, we've got a rectangle here, AXCC. Now what I want to show is that the area of this triangle turns out to be half the area of that rectangle. Now here's where we have to be a little careful, because the picture can look several ways. B could be at X, it could be at Z, it could be over here so that X is between B and Z, it could be in here where B is between X and Z, or it could be over here where Z is between X and B, and we need to make sure that our method and our proof works in all those possible cases. So we're going to start with the easiest case first, and that is when B and X are the same point. Now what we see here is that we actually have a right triangle right here with a right angle there at A, which is also Y. And we know from our properties of, well, just parallelograms, that when we draw a diagonal, we get two congruent triangles here. And that's certainly true for rectangles. So these two triangles, two right triangles here, that's the triangle BAC and the triangle CZB, have the same area because they're congruent triangles. Now we know then the area of that rectangle is then just the area of those two triangles, because it's that those two triangle interiors partition the interior of that rectangle. So we know the area of our rectangle is then 1/2 of that. So if we call this length here h, which is the common length distance between these two parallel lines, so it's the length of this altitude from the opposite side B to the line containing the base here AC. So there's our height. So we see that it's 1/2 the base times the height, and we get that set up. Now, what about if it's over here at Z? If B is the same as Z, that's case 2. Well, really, this is the same proof as we just did. Once again, we have a rectangle. We got two right triangles there. Each of the rectangle is base times height for the area, and each of those triangles then has 1/2 of that. Next, let's look at case 3. B is between X and Z. Okay, if we're in here, then once again, we're going to be looking at this. In this case, we can see it a couple of different ways. One of the ways we can do it is see that we can find the area here as the area. So the area, again here, of this triangle ABC is just the area of a right triangle here, AYB and CYB. So we just add the areas of those two right triangles. Well, from our cases 1 and 2, we see that the area of any right triangle is just going to be 1/2 base times height, or in other words, 1/2 the product of the lengths of its two legs. So here we have AY, that distance, times the height times a half, plus CY times the height times a half. Well, we just factor, here it is right here, 1/2 AY times height plus 1/2 YC times the height. we can factor out the h and the 1/2 using the distributive property, and then we have ay plus yc, but since y is now between a and c, that's going to make the same distance as the original base b. So once again, it's 1/2 base times height. Now, this is the hardest case here. Okay, so here, instead of, taking the triangle and trying to divide it up, it's going to be easiest if we look at the overall rectangle on the outside. Okay, so in this case, we're going to let d be this distance from a to y, which is also the same as from b to x. I believe that's what I've got here. D equals ay equals xb. And remember that from x to z, since this is a rectangle, is going to be the same as the distance from a to c. So that's also b. So if we go all the way from b to z, that's d, this distance right here, plus b, the distance here. So the area of the rectangle then is b plus d times h. Okay, but then the area of the rectangle is the area of these three triangles put together. There's our original triangle that's shaded here, that area, triangle ABC, and then these two new right triangles, which we already know how to find the area of, triangle AYB and triangle CZB. Okay, so if we solve for the area of our triangle, the area of our triangle then is the area of the rectangle. That's this big one from Y to B to Z to C. Okay, that rectangle, which is 1/2 B plus D times H. Okay, minus, it's not 1/2 there, it's just B plus D times H. It's a rectangle, no 1/2. Okay, and then minus these two areas here. So the first one is AYB, that's this one here. Well, remember we called this distance D and this distance H. So they're not necessarily the same. There's D and there's H. Okay, so that's going to be the area of that one. So it's 1/2 D times H. Now what about this bigger triangle here? Well, this is D plus A times H times 1/2. And so we're right here now. The area of triangle ABC is B plus D times H minus 1/2 DH minus 1/2 B plus D times H. Okay, let's see if we can work with this. Distribute the H here. That's B times H plus D times H. And distribute the 1/2 H here. We get 1/2 D at BH, put it here, minus, and then minus 1/2 DH. Okay, so minus 1/2 DH minus another half DH is minus 1 DH plus DH is 0. BH minus 1/2 of BH is 1/2 BH. And look at that. Once again, we get the area of that triangle is 1/2 base times height. And there's one last case to consider is when the B's over here, but that case just looks just like the last one. We take the area of that rectangle. Again, if we let this distance be the D now, and this is B, you've got a triangle here and a triangle here, plus the triangle here makes the big rectangle, and then the arithmetic is exactly what we had here if you just labeled the D the right way there. So, in all cases, what did we find? We found the area of the triangle was 1/2 the base times the height. The base is the length of one of the sides. The height is the length of the altitude, that is the distance from the other vertex, the opposite one opposite the base, perpendicular to the line containing the base. That line segment there, that line segment is called the altitude, and its length is called the height when this is the base. So here's a rectangle that we found with the same base and the same height. We know that the area of our triangle is 1/2 the area of that rectangle, whether the base B is at a vertex of that triangle inside of it or outside of it. It's still area of that triangle is 1/2 the area of the rectangle. Okay, well, wait a minute. Does it matter what side we picked for the base? Well, no, it doesn't. The sides were just kind of arbitrarily labeled anyway, so the exact same proof works if we'd started with a different side, just change the labeling, and it would work out. And you can see here that for the numbers, we've got the numbers worked out here. It doesn't matter which side that we pick. So for example, here we see that our original base was 4.7 and the corresponding height was 1.54. 1/2 times 4.7 times 1.54 is 3.63. These things have been rounded off, so that should work out for you. But if we take this side as the base of 6.04, its corresponding height is from the other vertex, opposite vertex, perpendicular here to that side, or to the line containing that side at least, and that's the height that goes with that base. So that base times height times 1/2 is also 3.5. And if we go to the third choice, where we let this one be the base from C to B, then the height is from this side perpendicular to that line, and that's going to be the height here at 3.76 when the base is 1.86, and you multiply those and you get 3.5 again. So it doesn't matter which side is chosen as the base, that will work out. Okay, so now we're going to use this to look at parallelograms. So start with any parallelogram. Here we go. And what we can do is just draw a diagonal. If we draw a diagonal, it cuts it into two congruent triangles. That's a property we know about parallelograms. Well, since each of those two triangles, that's a triangle ABC and triangle ADC, are congruent, then actually not in that order. ABC is congruent to CDA. We get it in the right correspondence. But in any event, those two triangles have the same area. So the area of the parallelogram is going to be twice the area of one of those triangles. Well, if we draw a perpendicular down, again, it's the distance between two sides here. So notice that one of the sides is a base of one of those triangles, and the height of that triangle is the same as what we call the height of the parallelogram. That's the distance between these two parallel sides, and that's the height that we have here. Well, 1/2 base times height will be the area of that triangle ADC, and it's the same as the area of this other triangle up here, CBA. And so the area that we're looking for is 1/2 of that, which is just twice that, excuse me. So it will be 2 times 1/2 times base times height, which is just base times height. And so that turns out to be what we get there. There are some other ways to see this. In the configuration that we have this one here, it's pretty easy to see that if we'll take this right triangle here and cut it off, we can slide it over here and fill in this one. We know they're congruent because, let's see, we know opposite sides of a parallelogram are congruent. We know these are right angles here and here. And let's see, what else do we know? We know the heights are the same. So that by the hypotenuse leg theorem, or big S, little s a theorem, hypotenuse leg theorem, these two triangles are congruent. So if we cut this area off here and scoot it over here, we'll get an area of a rectangle, AXYB, and we know the area of it. Well, when we scoot this over here to here, this is still the same base, or where it's up here, and then the height is still the height here. So it's base times height. Now you have to be a little careful using that as your actual proof, because you can get a shape that looks like this. Let's see here. Let's do this one here and do that. Now it gets a little bit more difficult to try to do the same proof here. So there are some cases here we might be able to work through those, but since I worked through all the possible cases for the triangle first, then I can use that for the parallelogram. If we could work through all the possible cases here, we'd have to be careful with that. And then we could prove the triangle by showing that any triangle that you start with, you just rotate around the midpoint of one of the sides, and that turns it into a parallelogram, which has twice the area. So the area of the triangle is 1/2 the area of the parallelogram. But the way that we proved it in this particular one is that we started with the triangle. So once again, the area of the parallelogram is just base times height, no 1/2 this time. It's the same as the area of that rectangle, which has the same or congruent base and that height. And it also is independent of which side that we pick. If we make a rectangle with this as the base and the height going this way, that would be the same as well. So now we should have formulas for the area of a rectangle, base times height, and of course that's going to be the same as for a parallelogram, because after all, a rectangle is a parallelogram, and the parallelogram turns out to have the same area. And then, of course, then we got the area of a triangle then to be 1/2 base times height. Turns out to be half the area of that rectangle. All right, and we can use these formulas now then to go and look at other figures, like trapezoids are a pretty interesting one. We might look at that one next.